Here's another example of attaching frames to links and finding the DH parameters. This time we're going to include prismatic joints. So for this example, we need to assign frames 0 to 4 for the shown RPR robotic arm, then find the DH parameters table. So RPR stands for revolute, prismatic revolute, and we can see the figure here. So the first joint here is a revolute joint that rotates about this axis right here. So that's a revolute joint. Okay. The second joint is a prismatic joint that goes along this line here. So the joint itself has a variable of d instead of theta. And then the third joint is a joint here, revolute joint, and that goes around this way about this axis. Okay, so you need to find, first assign the frames and then find the DH parameters. Okay, to start the solution here, again, I'm going to look at theta 1 and D2 and theta 3. These are the three joints, revolute, prismatic, and revolute joint. And then here we have L1 length or height, and L2 here and L3 here. So the way I'm going to start, as usual, I'm going to start with the z-axis first for all the joints, and then I'll go to x-axis for all the joints, and then the y-axis for all the joints. I'm going to start with z1 and z2 and z3, and then I'll do the special cases for z0 and z4, and then I'll move on to x1, x2, x3, and then go back to the special cases for x0 and x4, and then I'll do y0 through y4. Okay, so I'm going to start now with the z-axis, z1. Z1 is the axis of motion for the first joint. Since I have a revolute joint, this is the revolute joint here, rotates in this direction. And the axis of rotation is this axis that we see here, the dotted line. So that means this axis would be my Z1 axis. And again, I can choose either go forward or up or go down. So I can do either of these choices. In this case, I'm going to choose to go up for Z1. So I drew the Z1 here. Okay, that's my Z1. Now for Z2 is the axis of motion for the second joint, joint 2. Second joint is a prismatic joint that moves this way. Okay, so the axis of motion is the axis that moves this in that fashion. So this line here would be the Z2 line for joint 2, which is the axis of motion for joint 2. Okay, so I'm going to draw Z2 right here. All right. Now for Z3, that's the axis of motion for the third joint. The third joint is a revolute joint, this joint right here, and it rotates about this axis. Okay, so again, I'm going to draw this axis for the rotation about joint 3. So again, all these Z's, Z1 and Z2 and Z3, they can be drawn in either direction. So I can put Z1 upwards or downwards. I can assign Z2 to the right or to the left, and I can assign Z3 to the right, to the left as well. Okay, your choice. It doesn't make any difference. But consistency is important. So here, if I put Z2 this direction and Z3 in the same direction, that means I'm eliminating a twist angle. Where if I put Z3 the opposite direction, that means I'm creating a twist angle of 180 degrees. So that would affect my calculations and makes it a little longer, okay, unnecessarily. So in this case, if I put both of them the same direction, that would help me eliminate that twist angle between them. Now I'm going to go back to Z0. Z0, we assign it usually the same as Z1. So it will be at the same line as Z1. So I'm going to assign Z0, as you see here. And then for Z4, it's going to be, again, we can do it arbitrary, just like Z0, but it's always a good idea to do it from or intersecting with the end effector point, but at the same time make the Z the same direction as the previous Z, so that we can eliminate the twist angle. All right. So in this case, I'm going to start it from here and move in this direction, similar to the Z3 direction. All right, that would be my Z4. Okay, so all these Z-axes are assigned now, and as you can see, Z2, Z3, and Z4 are all sharing the exact same line, and Z0 and Z1 are sharing the same line as well. Okay, now we move on to the x-axis, starting with x1. x1 is the common perpendicular between Z1 and Z2. Okay, so this is Z1 and this is Z2. As you can see, they are both intersecting. When they intersect, that means x1 will have to be starting from the same point of intersection. And usually we have to make x1 go to the direction of Z2. But since both of them are intersecting here, it doesn't matter which direction we choose. So that means x1 can be either in this direction or in that direction. Either direction is fine, as long as it's perpendicular to the plane that has Z1 and Z2. So obviously Z1 and Z2 are on the plane of the screen, which means that x1 will have to be going into the screen or out of the screen. Okay, since this drawing is a 3D drawing, I'm gonna just draw x1 3D, and I'll have it going into the screen. Okay, so this is my x1 right here. I just removed the joints indicators here, just to make the chart here a little more clean for drawing the x-axis. So again, x-axis x1 is the common perpendicular between Z1 and Z2. Since both of these Z's are intersecting, that means x1 will be common perpendicular to both of them and can be in any direction. So you can choose this direction or the opposite direction. Okay. Now for x2, it's the common perpendicular between Z2 and Z3. Obviously, what you see here, Z2 and Z3 are the same line. So that what that means is that any line that's perpendicular to the Z line, both of these Z's, would be candidate for the x-axis. Okay, so I can make x-axis here in this direction or in any direction as long as it's perpendicular to this line, and I can also initiate it at any point along this line. Okay, because Z2 and Z3 are the same line, so they have infinitely many points of intersection. All right, so I can literally put x2 anywhere along this line, which means that would make the origin of frame 2 for me. Okay, and then from that origin I can put x2 from there. All right, so for this example, I'm going to choose x2 to be similar to x1. Okay, so I'm going to draw it at the same line, but then x2 will depart from x1 as soon as we move joint 2. This is a prismatic joint. So x1 is attached to link 1. Okay, so when the prismatic joint moves, x1 will not move. However, x2 will move because it's attached to frame 2. Okay, frame 2, which is on link 2. So I will draw it initially here as similar to x1. Okay, so x1 and x2 are the same line, the way you see it right now. But as soon as joint 2, which is a prismatic joint, as soon as it starts moving, x2 will depart away from x1 and move either forward or backwards, depending on the motion of that prismatic joint. All right, so that's my x2. But remember, x2 can be drawn anywhere on this line as long as it's perpendicular to the Z2 and Z3 line. All right, so now the origin of frame 1 is here, and the origin of frame 2 is also here. And again, as soon as joint 2 starts moving, the origin of frame 2 will move along with link 2. All right, now going to x3. x3 is the common perpendicular between Z3 and Z4. this is Z3 and this is Z4. As you can see, they are the same line. Again, that means we have infinitely many points of intersection between Z3 and Z4. Okay, so this means that any line that's perpendicular to the Z3, Z4 line would be a common perpendicular. So any line that we can draw anywhere, it can be here, it can be here, it can be here, and it can be pointing anywhere in any direction as long as it's perpendicular to the Z3, Z4 line. Okay, so that would provide me with an origin for frame 3, and I can also choose the direction for x3 from that point. So for this example, since we are given some dimensions here, I'm just going to choose my x3 to be starting at this point, which makes this point the origin of frame 3. Okay, now since I chose this point, now I have to choose the direction for x3. Again, it can be any direction as long as it's perpendicular to the Z3, Z4 line. All right, so I'm going to choose the same direction as the x2. This way we can eliminate an angle, make it 0, which is the theta angle between x2 and x3. And we'll see this in the DH parameters once we get there. All right, so I'm going to start my Z3, my x3 from here and go in the same direction as x2, as you see right here. Okay, but remember, we had a lot of choices to choose both for the origin of frame 3 and the direction of x3. Now we move on to x0. X0 is the common perpendicular between Z0 and Z1. Obviously, as you see here, they're the same line, Z0 and Z1. So that means I can choose my x0 to be anywhere along this line, and it can be in any direction as long as it's perpendicular to the Z0, Z1 line. Okay, now again, if I want to eliminate some of the calculations and make things easier, I would choose x0 to be the same as x1 when joint 1 is 0. Okay, so we can assume that when joint 1 is 0, x0 is going in this direction, same direction. Okay, so this makes my x0 here, and again I can choose the origin for frame 0 either here or anywhere along this line, but I'm going to choose it here so that all the kinematics can be in reference to the ground or floor point. All right, so that makes my x0 right here. Now moving on to x4, again we can choose this arbitrary as long as it's perpendicular to z4, but in this case it's helpful to choose it along the same direction as x3. This way we can eliminate a theta between x3 and x4. So we can choose it going starting from this point, which is the point of interest at the gripper or in the effector, and it will be pointing the same direction as x3. Okay, so that would be my x4. Now we're done with the x-axis. We're going to move on to the y-axis, and we are going to use the right hand rule. So using our right hand, I'm going to point my thumb towards z0, and then my forefingers towards x0, and then I'll move my forefingers 90 degrees, so that would give me an indication where the y direction is. In this case, it will be in this direction. Okay, so as you can see here, my thumb is towards z0, my forefingers is in the direction of x0, and then if I move 90 degrees, that would take me to this direction here for y0. Okay, this is a 3D plot, so this x0, if you think about it in 2D, this x0 will be going into the screen, and also x1 and x2 and x3 and x4 will be going into the screen if you look at this drawing in 2D. But because it's 3D, we are able to show these x-axes. Now we move on to y1. Again, I'm going to put my thumb in the z direction, my forefingers in the x1 direction, and then I'll move my forefingers 90 degrees so that it will point towards where my y1 should be, and that would be along this line here. So that would be y1 direction. All right, Now for y2, I'll put my thumb along z2 direction and my forefingers along x2 direction, and then I move my forefingers 90 degrees to point towards the y2 direction. So if I do that, then the y2 will be similar to the z1 direction. So I'm going to draw it on top of z1, and that would be y2 direction. Now again, I want to emphasize on this, these may seem to be all in the same point, but as soon as we move joint 2, frame 1 will stay in its place, and then frame 2 is going to move in the direction of motion of joint 2. Okay, so x1 and x2, y2 and z1, all of them will be departing from each other as I move joint 2. Now we move on to y3. I'm going to point my thumb towards z3, this direction, and my forefingers towards x3, this direction. And then I move my fingers by 90 degrees, and that would give me the direction for y3, which would be this direction up here. Okay, so that would be my y3. And then for y4, again, I put my thumb in the z4 direction, and my forefingers in the x4 direction. Then I move my forefingers 90 degrees, and that would give me the direction for y4, which would be this direction right here. So I'm going to draw y4 right here. All right. And that completes my frame assignments for this robot. Now we're ready to go ahead and extract the DH parameters. So I'm going to put my quick reference chart here for the DH parameters, and I'm going to put a table here that I can fill for the DH parameters. Okay. Again, this is alpha, A, D, and theta. Alpha and A are link parameters. D and theta are joint parameters. Okay, so when I equals to 1, this line here, I'll be looking at the parameters for joint 1 and link 1. So the link joint pair number 1. And then when I equals to 2, I'll be looking at joint 2 and link 2 parameters, and I'll place them right here. When I equals 3, I'll be looking at joint 3 and link 3 parameters. I'll put them right here. And then when I equals 4, I'll be looking at frame 4 parameters, since, well, of course, we don't have joint 4 and we don't have link 4, but you know, the frame 4 parameters will go in here. So let me start with the first alpha. When I equals to 1, I'll be looking at alpha I minus 1, so that would be alpha 0. This is the chart for alpha. If I'm looking for alpha 0, I should be look at z0 and z1 about x0. Okay, this is z0, this is z1, and I'm looking at the angle about x0, which is right here. Okay, so obviously z0 and z1 are the same line, so the angle between them about x0 would be 0. So that means alpha 0 will be 0. I'm going to place that here. Now when I equals to 2, I'll be looking at alpha I minus 1, which is alpha 1. So for alpha 1, I should be looking at z1 and z2 about x1. Okay, this is my z1 and this is my z2, and I'm looking at the angle between them about x1. Okay, so the way I have to find the angle, again, it can have a positive or negative sense. I'll have to put my thumb along the positive direction of x1, my forefingers along z1, and then I'll move my forefingers into the direction of z2, and then see how much did I move my fingers. Okay, my forefingers. So obviously if I put my thumb along x1, my forefingers along z1, then to go to z2, I'll have to move my fingers positive 90 degrees. Okay, positive 90 degrees between these two. So that gives me the angle between z1 and z2 about x1. That means alpha 1 will be positive 90 degrees. Now when I equals to 3, I'll be looking at alpha I minus 1, which is alpha 2. For alpha 2, I should be looking at z2 and z3 about x2. Okay, so Z2 is right here, and Z3 is right here, and I'm looking at the angle between them about x2, which is right here. Okay, so obviously Z2 and Z3 are the same line, so the angle between them about x2 would be 0. Okay, so that means my alpha 2 is 0. I'm going to put 0 here. Now when I equals to 4, I'll be looking at alpha I minus 1, and that's alpha 3. So for alpha 3, I'll be looking at Z3 and Z4 about x3. This is Z3 and this is Z4. The angle between them about x3, which is right here. Obviously Z3 and Z4 are the same line, so the angle between them about x3 would be a 0. So I'm going to put a 0 right here. Okay, now let me comment on this. Remember when we said that the z-axis can be in either direction? So let's assume that I put Z3 here in the opposite direction, pointing to the left. Okay, that means the alpha between Z2 and Z3 will be 180 degrees. Okay, which is this alpha right here. All right, and then the alpha between Z3 and Z4, remember if the Z3 is going to the left, so the alpha between Z3 and Z4 about x3 will be 180 degrees, which will be right here. Okay, so by putting all these in the same direction, we actually forced this alpha 2 and alpha 3 to zeros. And we're going to see later on how this affects our forward kinematics. Each one of these numbers will be calculated in a matrix. So if we have as many zeros as possible, that eliminates a lot of the calculations that wouldn't be necessary. All right. So we're done with the alphas. Let's go on to the a's. So when I equals to 1, I'm looking at ai minus 1, which is a0. This is the chart for a. For a0, I'll be looking at z0 and z1 along x0. This is z0, and this is z1 along x0, which is right here. So obviously the distance between z0 and z1 is 0 along x0. Okay? So that means my a0 would be a 0 right here. When I equals to 2, I'll be looking at ai minus 1, which is a1. So for a1, I'll be looking at z1 and z2 along x1. This is z1 and this is z2. I'm looking at the distance between them along x1, which is this line right here. So obviously x1 and x2 are intersecting, and the distance between them along this line would be 0. Okay, so my a1 would be 0 right here. Now when I equals to 3, I'm looking at ai minus 1, which is a2. So for a2, I'm looking at z2 and z3 along x2. This is z2 and this is z3 along x2, which is this line. Obviously z2 and z3 are the same line, so the distance between them along x2 is 0. Okay, so that makes my a2 equals to 0 right here. And then when I equals to 4, I'm looking at ai minus 1. That means a3. Going back to the chart here, a3, I should be looking at z3 and z4 along x3. This is z3 and this is z4 along x3, which is this line. Obviously z3 and z4 are the same line, so the distance between them along x3 is 0. So that makes my a3 equals to 0 right here. All right, that completes the A column. Now we move on to the D column, and this would be interesting and different from the previous examples, and we'll see why. Okay, so when I equals to 1, I'm looking at di, which is d1. I go to the D chart here. So for d1, I'll be looking at x0 and x1 along z1. Okay, this is x0 and this is x1 along z1. This is z1. Okay, so obviously there's a distance between x0 and x1 along z1, and this distance is constant, it doesn't change. Okay, and that distance is indicated here as L1. Okay, so that means D1 equals to L1, which is a constant. Okay, we are expecting a constant, so each one of these lines we are expecting one variable for the joint variable. Okay, and in this case this first line includes a revolute joint. That means the variable is going to be the theta, not the d. Okay, so this will be a constant. Now when I equals to 2, I'm looking at di, which is d2. So d2, I'll be looking at x1 and x2 along z2. This is my x1, okay, and also it is my x2. I'm looking at the distance between them along z2, which is this line. Okay, so the way it's drawn right now, it looks like x1 and x2 are the same line. But remember, as soon as joint 2 starts moving, frame 2 will move along with it, which means that x2 will depart from x1. Okay, so that point becomes further and further away from x1. So that distance between x1 and x2 along z2 is a variable, and that variable changes as we change the value for joint 2, which is a prismatic joint. Okay, so this means I'm going to put this as d2, which is the variable for the prismatic joint. So I'll put it here as d2. So this is a variable, all right? This means that we're expecting that the theta for theta 2 here to be a constant, all right? Since the variable is right here for prismatic joint, that means this would be a constant. And since this is a constant for the revolute joint, joint 1, this will have to be a variable. And we'll see this once we start working on this column. All right, when I equals to 3, I'm looking at di, which is d3. So for d3, I'll be looking at x2 and x3 along z3. This is x2, and this is x3, and I'm looking along z3. Okay, so obviously there's a distance between this point and this point. And even remember, even if we move joint 2, x2 is going to move along and x3 will move as well. So this distance will never change between x2 and x3. Okay, and that distance here is indicated, as you can see here, by L2. All right, so that means the distance between x2 and x3 along z3 is L2. So I'm going to put L2 here. Now when I equals to 4, I'm looking at di, which is d4. And for d4, I'll be looking at x3 and x4 along z4. This is x3, and this is x4 along z4, which is just this axis right here. And obviously there are no joints anywhere here. This is attached to frame or link 3. Okay, this is link 3. So there's no change, and there's nothing is going to be changing between frame 3 and frame 4 at all, since there is no joint between the two. All right, so that distance between x3 and x4, these two axes along z4, is a constant, and that constant is L3 as indicated here, from here to here. Okay, so I'm going to put L3 here, which would be d4. All right, that would finish our d column. Moving on to the theta column. So when I equals to 1, I'm looking at theta I, which is theta 1. This is the theta chart. So for theta 1, I'm looking at x0 and x1 about z1. This is x0, and this is x1, and the angle between them about z1, which is right here. Okay, so the way they look right now, they look like they have the same direction, but as soon as I start moving joint 1, remember joint 1 rotates this way, okay, about this axis z1. So as soon as I start moving joint 1, xz is attached to the ground, so it's not going to move, and x1 is attached to frame 1 and link 1, so it's going to start moving back and forth this way, okay, along with the motion of theta 1. So that means this angle between x1 and x2, x1 and x0 about z1 would be a variable, and that variable will be theta 1, which is the joint angle for the first joint. So I'm going to put it here as theta 1. All right. When I equals to 2, I'll be looking at theta I, which is theta 2. So for theta 2, I'll be looking at x1 and x2 about z2. This is x1 and it's also x2. And I'm looking at the angle between them about z2, which is this right here. Okay? So if you look at it right now, they are the same direction. And even when we move joint 2 is a prismatic joint. Even if it starts moving back and forth, the angle between x1 and x2 about z2 will never change. Okay, this is prismatic, it only moves right and left, it does not rotate. Okay, so that means the angle between x1 and x2 is 0. The angle about z2 is 0. So that means theta 2 equals to 0. I'm going to put 0 here. Now when I equals to 3, I'm looking at theta I, which is theta 3. So for theta 3, I'll be looking at x2 and x3 about z3. This is x2 right here, and this is x3 right here, and the angle between them about z3. Alright, so the way they look right now, they look like the same direction, but as soon as I start moving the third joint, it's a revolute joint, as soon as I start moving this, frame 3 will move and rotate with the joint. So that means x3 will start rotating back and forth with joint 3. Okay, and that will create a variable angle between x3 and x2 about z3. Okay, so that angle between x2 and x3 about z3 will be a variable, and we're going to call this variable theta 3. We're going to put it right here. When I equals to 4, I'm looking at theta I, which is theta 4. So for theta 4, I'll be looking at x3 and x4 about z4. This is x3 and this is x4. The angle between them about z4. Obviously there's no joint here and they're both in the same direction, so that angle between them will never change. And as it looks right here, it looks like the angle is 0. The angle between x3 and x4 about z4 is 0. Okay, so that makes my theta 4 equals to 0. So I'm going to put it right here. Okay, so that completes my DH parameters, and I want you to pay attention to this. Look at each line separately. Each line has 3 constants and 1 variable, except the line that we have the gripper, since the gripper does not have a joint. Okay, so if you look here, the first 3 elements are constants, and this is a variable because we have a revolute joint. Okay, and then for the second line, we have the first 2 elements are constants and the fourth element is constant, but the third is a variable, which is D. And this is because we have a prismatic joint here for joint 2. For the third line, we have the first 3 elements constants and the fourth element variable, and that's because our third joint is a revolute joint. Okay, in the fourth line here, all of them are constants simply because we do not have a joint at the fourth frame. Okay, so since there's no joint, all these parameters will be constants. And now we're ready to go further with forward kinematics once we find the DH parameters, and we'll see how we can do that in later slides.